40th lecture or more about spectral density. Before I start today's lecture, there was a question in the class and I left you in some kind of a suspense regarding the joint probability density of two events. The events being from two different random processes. You recall that we wrote in the definition of the cross correlation function p x y, we said not equal to p y x, although the time difference is the same. Are you still in dark about the explanation of this, or okay? The point is something like this. If I draw the picture, it should be immediately obvious. Suppose x of t and y of t, these are two samples from two random processes. Let us say x of t is like this and y of t is like this. Some arbitrary random function, t versus t. And suppose we fix our t1 somewhere here. Let us say this is t1, this is t1, and t2 is somewhere here, t2. When you say the joint probability density, well, if our x1 is defined at t1, y1 is defined at t1, similarly x2, the other random variable, is defined at t2 and y2 is defined at t2, then what we are talking about is if x is at t1 and y is at t2, then the probability density is of this random variable with this random variable, okay, x1 with y2. On the other hand, if we interchange this, t1 and t2, the difference or absolute values of the time remaining the same. When we interchange the two, then we are talking of y1, that is y at t1, and x2, that is x at t2. Obviously, this random variable and this random variable, they are not the same as x1 and y2, and therefore their probability densities shall be different. What is meant by stationarity in this context is that if you change the time frame, that is t1, t2, suppose these are two rods like this, all right. If you change them along the t-axis, keeping the difference between them the same, the probability density function does not change. This is what is meant by stationarity. But when you are talking of pxy, you are talking of px1, y2. When you are talking of pyx, you are talking of y1, x2. This combination of random variables is quite different from the combination that you have taken here, and therefore the probability densities in general are not equal, and rxy is not equal to r of yx. They are different.
But the characteristics of x1 will be the same as the characteristics of x2.
That is okay for the same process.
Right.
But we are talking of the probability of this event and this event occurring simultaneously, and therefore it is different. Okay? So that was the explanation. It was simple enough, but I wanted you to find out something by yourself. Now, about spectral density, we saw how we defined the spectral density. We took a random time function and then truncated it between minus t and plus t, ut minus t, and we called this as x truncated version of t. Capital T, capital twice t is the length of the gate, minus t to plus t, and we saw that under this condition we could define a Fourier transform x t omega as minus infinity to infinity x t of t e to the minus j omega t dt, and that under this condition one could define this function, that is e x t omega squared divided by 2t under the condition that limit capital T tends to infinity. Is that the definition? this was defined as the spectral density Sx of omega, and then we saw that Sx of omega is very elegantly related to the mean squared value of the process. In fact, the mean squared value, that is x squared bar, was equal to 1 over 2 pi integral minus infinity to infinity Sx omega, yes, d omega. Okay, they are very nicely related to each other. Now, in practice, what we need is not Sx of omega, but the analytic continuation, mark my words, analytic continuation of Sx of omega to the complete S plane. This omega is the imaginary axis of the S plane. What we want is Sx of S by j. That is, from omega we want to go to S by j, and there are reasons for this, because going to S by j, going to the complete S plane, allows us to make some calculations, some computations more easily than if we confine ourselves to the j omega axis. And to distinguish between the functional forms of Sx and Sx, we shall call this as this Sx. Well, why don't we make a distinction? Let's say dollar sign of S, all right. We shall call this Sx of small x. Why is this important? But before this, how do we do this? All that we do is omega we replace by small s by j. So, omega squared, now you know that the spectral density is an even function of omega. It is positive. What are the other? It is positive. What else? It is even. Anything else? There are three qualities attached to the spectral density. Pardon me? It's real. It's real.
Even and positive.
Even and positive. Well, we can say non-negative. It could also be 0. All right, non-negative. All right. If that is so, then obviously, and Sx of omega is a rational function. That is, it is a function like this: summation ai omega to the 2I divided by summation bi omega to the 2I. Then all that you have to do to obtain Sx of s is to replace omega squared by minus s squared. That is, you shall have to write ai minus s squared to the power I divided by summation bi minus s squared to the power I. All right. Now, what are the properties of this function Sx of s, which is an analytic continuation from the j omega axis to the complete S plane? We illustrate this with the help of an example. Suppose Sx of omega equals to 10 omega squared plus 5 divided by omega 4 plus 10 omega squared plus 24, let's say. Then my analytic continuation becomes 10 5 minus s squared divided by s to the 4 minus 10 s squared plus 24, which I can write as 10 5 root 5 plus s root 5 minus s divided by what can I write about this? S squared, 4 and 6. So, s plus root 6, s minus root 6, then s plus 2 and s minus 2. All right. Now, you notice that the analytic continuation can be, it's a rational function in S, and therefore, it can be represented by its poles and zeros. And you notice that the zeros occur in symmetry around the j omega axis, all right. There is a 0 at root 5 and there is 0 at minus root 5. Similarly, the poles also occur symmetrically with respect to the j omega axis. Now, the poles and zeros which are in the left half plane are called left half plane poles and zeros, and those in the right half plane are called right half plane poles and zeros. Now, for reasons to be made clear, we shall write this slightly differently. What we will do is, we will write this as minus s minus 10, then I will write this as s minus root 5, okay, and this therefore I shall write as k, some constant k, then I write n of s, n of minus s divided by d of s, d of minus s. Is that clear? This is to be able to identify n of s and d of s. That is the factors, the numerator polynomial is being broken up into two factors, one of which has zeros in the left half plane, the other has zeros in the right half plane. Similarly, the denominator is broken up into two parts. D of s has zeros in the left half plane, d of minus s has zeros in the right half plane. And obviously, your n of s by d of s, that is the ratio with poles and zeros in the left half plane, in this particular case is s plus root 5 divided by s plus root 6 multiplied by s plus 2. This is the part. And then you have to multiply this by n of minus s divided by d of minus s and a constant k. The constant in this case is equal to minus 10. No, it is minus 10. This is why I changed this. Oh, you were right. Oh, it was in the correct form, minus s plus root 5. But don't you have to change here? S plus root 6. Oh yeah, okay. K is equal to plus 10. All right. Why do we have to do this? Why do we have to change over to the S plane? This is because you recall the relationship between the mean squared value and the spectral density, capital S x of omega d omega. Now, if S x of omega is given, then the mean squared value can be found out from this integral. And this integral is often very difficult to perform in the omega domain. That is when S x of omega is taken as a real quantity. On the other hand, it becomes very simple if you change omega to s by j. You notice that this would be, if you say s x s by j ds, then this becomes from minus j infinity to plus j infinity, and here you have 1 by 2 pi j. You notice that this is a complex integration. This is a contour integration because it is an integration in the complex variable, and plus j infinity and minus j infinity. So, what we can do is we can draw a circle, a semicircle of radius infinity to in the right half plane, and take all the poles in the right half plane, find out the residues, that is apply Cauchy's, what is it called? Cauchy's residue theorem, to be able to evaluate this. And this is sometimes much easier to do than integrating in the real domain, integral minus infinity to infinity s x of omega. All right. It has some other ramifications also, which you will see later perhaps in the communication theory course. But for the present this it is for contour integration, convenience of contour integration, that one does that. All right. Now, suppose s x of s is of the form, forget about the constant multiplier. Let's say the spectral density continued analytically into the S plane is like this. All right. Then if the spectral density is a rational function, obviously this representation is that of a rational function. If it is irrational, we cannot represent it like this. N of s will not be a polynomial if it is irrational. All right. For such functions, if we denote 1 by 2 pi j integral minus j infinity to plus j infinity n of minus s divided by d of s d of minus s ds, and n of s is a polynomial. So let us say it is C0 plus C1s plus etc. plus, I will write the last term later, and suppose d of s is another polynomial which is let us say d0 plus d1s plus etc. Now if I write this as dn s to the n, that is the highest power is n, what can be the highest power in capital N of s? That is the question. Obviously the highest power cannot be the same as in the denominator. Why not? Because then x squared bar shall be infinity. What does it mean? It means that this relationship is not valid. All right. So this must be at least one less.
S of n minus.
Is at least one less, that is n minus 1. So at the most what we can have is Cn minus 1 s to the power n minus 1. At least one less. So one of the conditions for this method of calculating x squared bar is that degree of n must be less than the degree of d. It cannot be otherwise. All right. If the degree of n is equal to or greater than the degree of d, then x squared bar shall itself blow up, and therefore we cannot calculate this. Now let us denote this integral with d of s degree equal to small n as in. Then the values of in have been tabulated in the literature, and you can use those tables. In the textbook you will get up to small n equal to 3. And the expressions are very simple expressions. I1 n equal to 1, it is C0 squared divided by 2 D0 D1. I2 equal to C1 squared D0 plus C0 squared D2 divided by twice D0 D1 D2. No need to commit this to memory. You keep it at a prominent place. And I3 is somewhat lengthy. C2 squared D0 D1 plus C1 squared minus twice C0 C2 D0 D3 plus C0 squared D2 D3 divided by twice D0 D3 D1 D2 minus D0 D3, and so on. I3, I4, I5 for n equal to 1 to 10. These have been tabulated, and hardly ever in practice you require a calculation which goes beyond n equal to 10. And so one need not bother about the contour integral. If you have to do it, then you have to do it. There is no other way. All right. You locate, as I told you, you take your your contour as this. There cannot be a pole on the contour. Not my words carefully. This is the sigma and this is the j omega axis. Well, there is a break here somewhere. There is a break here, so that plus j infinity and minus j infinity, and the radius of the circle capital R tends to infinity. If you have to make contour integration, obviously there cannot be a pole on the contour, which means that there cannot be a 0 of, yes, ds on the semicircle. Well, obviously because the degree of d is 1 greater, at least 1 greater than the degree of n, so there cannot be a pole on the semicircle. That is guaranteed. But can there be a pole on the j omega axis? No, that is not also permitted. Why not? Because then you cannot do the contour integration. No, that's not quite true. If it is only a contour integration, then what we do is we go around this with a small indent. There is a different reason why a pole on the j omega axis is not allowed. At the pole, you see, if I have, let's say, s squared plus omega naught squared, as a factor in the denominator, then when omega is equal to omega 0, the complete function blows up. What are you going to integrate? And therefore x squared bar at x squared bar is again going to be infinity. So for the success of the contour integration, or for the success for using this table, there are three conditions therefore. What are these? One is that the degree of the numerator must be at least 1 less than the degree of the denominator. N degree should be less than the degree of the denominator. N and D roots in left half plane. We have chosen, what we did was we wrote n equal to C0 plus C1s plus etc. and d equal to d0 plus d1s plus etc. And this we considered the polynomials obtained by multiplying the left half plane root factors, and therefore n and d roots in left half plane, and no roots, this is number 2, number 1, and third is no roots of d on the j omega axis, that is no poles on the j omega axis. What about roots of n? Are they permitted? Can n have roots on the j omega axis? Yes, because then the function shall simply blow up at that particular, not blow up, it becomes 0 at that particular frequency. So we are not worried about it. After all, you are integrating with respect to omega, and therefore at omega equal to that particular value, it simply becomes 0. So this must be remembered, that if capital D, if there are poles on the j omega axis, then your procedure shall not be valid. You can still make a contour integration, isn't it? You can still make a contour integration, but that will not be meaningful in the context of the physical system, in the context of the signal that we are dealing with, all right. That is only mathematics, but the physical interpretation shall cease to be valid. To illustrate this, let us suppose that we have a random process whose spectral density is given by this, omega squared plus 4 divided by omega 4 plus 10 omega squared plus 9, and we used to calculate the mean squared value of the random variable. Okay, so the first thing that we do is we find out Sx of s, which you can see is 4 minus s squared, and therefore 2 plus s, 2 minus s divided by, we shall have here s to the 4 minus 10 s squared plus 9. So s squared minus 9 and s squared minus 1, and therefore I shall have s plus 3, s minus 3, and then s plus 1, s minus 1. Now what is your n of s? Obviously n of s is s plus 2, and n of minus, I am sorry, d of s is s squared plus 4s plus 3, s plus 3 multiplied by s plus 1, all right. So my C0 is equal to 2, C1 is equal to 1. I'm comparing with the coefficients of the numerator. D0 is 3, D1 is 4, and D2 is 1, all right. And all I do is I substitute these values in the expression for I2, that is integral with n equal to 2, and if you do that and calculate x squared bar, the mean squared value comes out as 7 by 24. Is the procedure clear? Do not worry about the negative sign. You see, it's not strictly d of s, d of minus s, isn't that right? In the denominator, what you have to do is minus s plus 3, that would be part of d of minus s, but there is a minus s plus 1, all right. Will this be true? Well, in this particular case the constant multiplier is 1, but suppose the degree was 6, then the multiplier would have been minus 1. This has to be kept in mind. Here it does not matter, but if it was otherwise, then you will have to take d of s, you will have to take s x of s with a multiplier of minus 1. Does that change the value of the integral? Yes, it does. Isn't that right? Because after all you are integrating s x of s. Is that okay? Right. You must be careful about this. Now we look at this function again, that is s x of omega. By definition, it is limit t tends to infinity, expected value of capital X t omega mod squared divided by 2t, which I can write as s x of omega limit t tends to infinity. Bear with me, it would be a longish kind of derivation and you must follow these steps. I write this as expected value of x t omega star times x t omega. Is that okay? Mod square is the quantity multiplied by its complex conjugate. Now I will write this I will write this separately and I will use two values of time for this. It does not matter, x t omega, after all I can write j omega e to the minus j omega t1 dt1, the variable of integration I can call it arbitrary, t, t1, t2, it does not matter, I can call zeta, xi, theta, whatever I wish. This is what I shall do, that is I shall write s x of omega as limit t tends to infinity 1 by 2t, then expected value of, first I will write integral minus infinity to infinity x t t1 some t1 e to the minus j omega t1 dt1 conjugate of this. This is what stands for. What does it stand for? Capital X t of omega star multiplied by integral minus infinity to infinity x t at some other instant t2. Alright, t2 is a dummy variable, e to the minus j omega t2 dt2, and then the square bracket. Alright. Now obviously if I remove the star here, the star means xt is a real quantity, dt1 is a real quantity, so all that happens is this becomes plus, and then I can combine the two, t1 and t2. Do you see the trick? I am not putting identical t's, alright, I am putting different t's. It does not matter because t1 and t2 are running variables, and therefore I can write this as limit t, let me write it in a separate piece of paper. Therefore, pardon me, the value of the integral will be the same because it is a function of omega. In this integral, t2 is a dummy variable. It can be anything. It is a definite integral, and therefore the value of the function, value of this integral shall be only a function of omega. I am doing this for a very specific reason which you shall see in a minute. I write this as limit t tends to infinity 1 by 2t, then what I do is, alright, let me keep the expectation sign still, integral minus infinity to infinity, let us first write t2 dt2, alright, the order of integration can be interchanged whatever way you like, then integral minus infinity to infinity, what we get is xt t1 multiplied by xt t2, alright, then e to the power minus j omega t2 minus t1, then dt1. Alright, have I missed something? No, I have kept everything. That is, I first integrate with respect to t1, and in this integral t2 is held a constant because they are independent of each other, and then I integrate with respect to T2. Limits are the same, minus infinity to plus infinity. Now in this I put now T2 minus T1 as some value tau, and what I do is I change this expectation sign. Expectation sign is over the ensemble, and therefore expectation sign can be brought inside the integral. That is, instead of here, I bring the expectation sign here. Well, then what is this quantity? Don't you see that this is the autocorrelation coefficient as a function of T1 and T2 if the function is non-stationary. Alright. So this is Rx of T1 and T1 plus tau. But if it is stationary, then it is Rx of tau. Alright. If it is stationary. Let's consider this as stationary. For a non-stationary process, the modification shall be obvious. And therefore, if T2 minus T1 is equal to tau, then dT2, alright, shall be equal to d tau for the second integral. Isn't that right? For the second integral, first I integrate with respect to T1, then I integrate with respect to T2. When I integrate with respect to T2, obviously it is T1 is a constant. So dT2 is equal to d tau. Now I can clear this mess and write in a more elegant fashion as follows. What I write is Sx of omega is equal to limit t tends to infinity 1 over 2t integral minus infinity to infinity d tau, instead of dt2 I write d tau, and then I get minus infinity to infinity Rx of tau e to the minus j omega tau dt1. Alright? Is that okay? Now you see that this quantity has now become independent of T1. One should remember, however, that tau is T2 minus T1, and therefore it is not quite independent. T1 still occurs here. But one thing to be noticed is the following, that one thing to be noticed is that T12, it is restricted to lie between, both T1 and T2 are restricted to lie between minus capital T and plus capital T. Therefore, this is less than equal to T. Alright? Which means that this integral, this second integral, well, both integrals in fact, not both integrals, because this is integral with respect to tau, that we shall come later. But this integral with respect to T1, well, it suffices to integrate with minus T and plus T. Is that okay? No? This integral with respect to T1, and small t1 lies between minus T and capital T. And therefore, it suffices to replace this minus infinity and plus infinity from minus T to plus T. Now, if I bring this 2T along with this integral, they will cancel. Which means that the limiting value will be independent of capital T. And ultimately what we will get is that this will be integral minus infinity to infinity Rx tau e to the minus j omega tau d tau. Is the logic clear? Argument? There are several steps that we are doing, but each is a valid step. We are not making any approximation. No approximation. It's just transformation of variables and recognizing that integration with respect to T1 exists only from minus capital T to plus capital T. And therefore, and this is a very well-known relation which says that the spectral density must be the Fourier transform of the autocorrelation function. This is the link that we did not recognize at the beginning. We defined a spectral density, then we have established the relationship that the spectral density, and this is the major use of spectral density, that it is the Fourier transform of autocorrelation function Rx of tau. Where is the transformability condition reflected in this relationship? On Rx of tau you can find out. Given a random process, you can always find out Rx of tau. Where is the Fourier transformability condition?
Rx of tau should be absolutely some integrable.
Rx of tau should be absolutely integrable, which means that we cannot take, we must restrict the value of the range of t, otherwise it shall not be absolutely integrable, which means that what we are restricting is the value of tau. Alright, so the transformability condition is still reflected here, and obviously then Rx of tau is the Fourier inverse of Sx of omega. In some random processes, it is Sx of omega which can be found more readily, that is the spectral density can be found out more readily than the autocorrelation function. In some situations, it is the autocorrelation function which can be found more readily. So in either case they are related by the Fourier transform relationship. And this is a big saving in computation. Not only big saving, the quantity that we defined artificially as the spectral density, 1 by 2t expectation of a truncated Fourier transform divided by 2t. Well, this has come out to be in a very elegant form, that is simple Fourier transform relationship. Let's take a few simple examples. One is that if Rx of tau, well, these are usual examples that one takes, is let's say a e to the power minus beta mod tau, which means that the plot of Rx of tau at tau equal to 0, it shall be discontinuous. Okay, this is tau, it shall be discontinuous like this.
It's not discontinuous. It's continuous but not differentiable.
Not differentiable at tau equal to 0. Alright. Now if I find out the spectral density Sx of omega, then obviously we shall have to find out from minus infinity to 0 plus 0 to infinity. And minus infinity to 0, capital A, yes, what shall be the form of the function? E to the?
The Fourier transform of this.
I am taking the Fourier transform.
We already know it, sir.
Oh, you already know it. Okay. So this is equal to twice A beta divided by beta squared plus omega squared. Yes, we know this already. Which means that that if I plot this, the maximum value of Sx of omega, it occurs at omega equal to 0, and the value is, yes, 2a by beta, and then it goes to 0 on both sides. This is the usual spectral density of noise. Alright, it's sometimes convenient to take the noise spectral density like this or some other process. But you shall encounter this autocorrelation function, that is autocorrelation function which exponentially decays on both sides very often. If it is not that of the process, well, it is taken to be approximately that of the process because it simplifies calculations. Now let's take the next example as white noise. I introduced this hypothetical concept. White noise Sx of omega is equal to a constant S0 for all omega. So what is the autocorrelation function? It must be S0 delta of omega, which is also
Tau.
delta tau. That's correct. I made a mistake. S0 delta tau. Now if it is colored noise, let's say we have a function like this. This is S0, this is 2 pi f0 minus 2 pi f0, and for the rest of it, it is 0. When f0 tends to infinity, this is the spectral density of white noise. Since it is band limited, we call it colored noise. Then if you take the take the inverse Fourier transform. We know how to,
Sync function.
it's a sinc function, and the result, I leave the algebra to you, Rx tau is equal to twice F0 S0 sine of, is it a sinc function? 2 pi F0 tau divided by 2 pi F0 tau. Is it a sinc function? Yes, it is. Okay. And you notice that if F0 tends to infinity, then this function itself tends to infinity. We can't say it's a delta function, yet it tends to infinity. And you can show that this function, sinc function, which is, which plot is something like this, sin x by x, so it goes like this. You are quite well acquainted with this. When f0 tends to infinity, what happens is, the main lobe, what happens to the main lobe?
So it narrows and
It narrows down,
and also its amplitude.
amplitude goes up, to, this goes to delta tau, as f0 goes to infinity. It is important that it's multiplied by f0. Just the sine function by itself doesn't do that. It must be multiplied by f0. The area under the integral must be equal to 1. The area under this integral is equal to 1, which is another way, which is a way to prove, to find out this integral. This integral is not a very simple, oh, it's not very difficult, because f0 and f0 cancel each other. Anyway, what happens is, this integral, this is equal to unity, irrespective of f0, and when f0 goes to infinity, it tends to delta tau. All right, now two more spectral densities. What we have done so far is spectral density of a single random variable x of t. If I take two random processes, x of t and y of t, then exactly like cross correlation coefficients, it is possible to define cross spectral density. And the definition is slightly peculiar. You will have to remember this, that it is the same kind of thing. It's an expected value, limit t tends to infinity, 2t, then instead of xt omega mod squared, it is the product of xt and yt, but one of them is complex conjugate. And the convention is that the first random process, complex conjugate of that is taken, that is xt star omega multiplied by yt omega. Okay? Expectation, yes. That's it. This is something which you have to remember. In other words, it's simply, the product is simply xt of minus omega, alright, because it's the complex, if x of t is a real quantity, then you know this complex conjugate of this is simply omega changes to minus omega, nothing else, multiplied by yt of omega divided by 2t, then limit t tends to infinity, expected value of this, and this is equal to s x y of omega. This is called a cross spectral density. Obviously now one can define another cross spectral density, that is capital S of yx of omega. If we do that, then we have to conjugate yt. Now something else that is to be noticed is that the truncation of both the random processes are to be done from minus t to plus t. That is, x of t as well as y of t, both of them have to be truncated from minus t to plus t. It is not under your control. Otherwise you cannot define a spectral, cross spectral density. ultimately it simply becomes a function of omega. Capital T, dependence on capital T disappears, because capital T ultimately goes to infinity. One can argue, why don't we take truncation from T1, minus T1 to plus T1 and minus T2 to plus T2 and allow both of them to go to infinity. Well, you will get identical results, but you unnecessarily complicate life. One should take both of them to be equal. Now, therefore, cross spectral density Yx of omega is limit t tends to infinity, expected value of Yt minus omega xt omega over 2t. 2t you can take outside, because expected value simply, no, not outside the limit,
No, just
inside the limit. Well, this is the way it is written, expected value either in the numerator or denominator. You notice that s yx and omega and x xy of omega, they are not necessarily equal. Not only that,
So there, when x minus, their mirror reflection.
oh yes, s of
Xy omega
xy omega is equal to
sy yx minus omega.
syx or minus omega. That is correct.
It's real.
No,
The functions are real.
Which
not
functions?
necessarily. Not
Y and x. Y, small y and small x. This random processes are real. But the spectral densities, cross spectral densities are not necessarily real. Why not? Because this is a complex conjugate of something else. So the product is not necessarily real. In other words, cross spectral density CSD is not necessarily real.
So it has to be real, sir.
Why?
So for a real function, the Fourier transform.
We can't say that. We could say this about spectral density of a single random variable. This is real. Not only real, it is real, non-negative and even. Can we say anything about this cross spectral densities? Well, we have shown that they are not necessarily real. They are not necessarily non-negative. They can also be, well, if they are not real, negative or positive does not mean anything. Isn't that right? Okay. Not only that, are they even? Are they necessarily even? Not necessarily. Alright. So, all those nice properties, elegant properties of spectral density for a single random process disappear. Cross spectral densities nevertheless are extremely useful. They are extremely useful, particularly when a signal is corrupted with noise. Y could be noise and X could be the signal. Alright. Now, it is however true that the real part of SYX or SXY, what can you say about this? Real part of this must be even. Why? Real part of this must be even, because this is a quadratic form. It is a Fourier transform multiplied by the complex conjugate of another Fourier transform. So, if you take the real part must be even, right? Can the real part be negative? Why not? It's very easy to make mistake. The imaginary part of this must be odd. All that we can say is this, nothing else. Regarding the sign or any other thing, you must be very careful. This is all that we can say. And if the processes are jointly stationary, that is x of t and y of t are jointly stationary, only then we can say that syx of omega shall be equal to the Fourier transform of r x, no, I beg your pardon, yx of tau, if they are jointly stationary, not otherwise. Okay. And similarly, if yx is replaced by xy, then this shall also be replaced by xy. Now, this is a lot of concept, but don't get confused between the spectral density for a single random variable and the spectral density for two random variables taken from different processes x and y. What for a single random variable, the spectral density has very elegant properties. It can be handled very easily, but whenever you are talking of a cross spectral density, you must be very careful. In the next lecture, that is Thursday, we talk of response of linear systems to random inputs, and you will see there how the spectral density comes into effect. That's all for today.